Okay, we are looking at section 1.7 for pre-calc. And in this section, we're going to be looking at some interesting relationships for actual modeling of what we're doing with each one of the relationships we've been studying. And if I can pull up my notes, there they are, hiding. After this section, I will be able to write functions from formulas, graphs, verbal descriptions, and data. Now, when we're doing this, you want to make sure that you're careful, but this is a lot of calculator use too, so we want to make sure that you can interface with your calculator, so I got mine up. So let's see what we've got. Number one, we're going to form functions from formulas. Example one, forming functions from formulas. Now as a reminder, I got circumference 2 pi r, area is pi r squared. Now write an area A of a circle as a function of its radius. Area as a function of its radius is pi r squared. Now, area as a function of its diameter, because a diameter is half a diameter is a radius. So as a function of the diameter, we're looking at half diameter squared for the area. And for those folks who are wondering where I came up with that, remember, this is one diameter, and there's two radiuses in it, because that's radius. Okay, now a radius is half a diameter. So I'm able to write this out this way, or I could actually finish it as pi times d squared over 4, or I could say finally pi d squared over 4. Now I'm also supposed to look at area as a function of its circumference. Now circumference is 2 pi r, and r is c over 2 pi. So if I'm looking at that, I can substitute r over c over 2 pi. And now if I take my area formula, I can put in c over 2 pi in place of r. So now I can square those, and I have pi c squared over 4 pi squared, but the pi's will cancel. So I've got c squared over 4 pi is my area in terms of circumference, or I should say area as a function of circumference in c. So these are the ways I'm looking at these equations, and well, we're just going to move on to the next one here. A maximum value problem. Now, in this problem, I'm using volume is equal to length times width times height. Okay, now in this maximum volume problem, a square of side x inches is cut out of each corner of an 8-inch by 15-inch piece of cardboard. So what they're saying here is I've got an x by x square cut out of each side. Okay, so when I fold this, I'm going to have this dimension to deal with. So my volume will be x times 8 minus 2x times 15 minus 2x. Now, a lot of folks are wondering, where did he get the minus 2x? This is one of the x's, this is the second, so this length is now 15 times 2x, which is this side. 15 minus 2x. And this side, if I can get the green, is 2x, but it's 8. This whole thing is 8, but I'm subtracting off 2x. That's what's this side. Now, that x part folds up, and it's my height here on my box. So that's my height. I've got my length, which is 15 minus 2x. My width is 8 minus 2x. And my height, which is just x. So that's my volume, my three measurements for volume. So I was supposed to write the volume V of the box as a function of x. Now find the domain of V as a function of x. Now we've talked about relevant domains. This function works all the time, but it doesn't make sense to have an x that's negative, or a height that's negative, or a length that's negative. So I have to consider what's going on. Okay, the largest x could be, when I'm looking at it, x has got to be greater than 0. I know that, but what are the limiting factors of x? So if I look at 8 minus 2x, that's got to be greater than or equal to 0. But there's just so much of that side. So if I consider solving that, I got 8 is greater than 2x, and I divide by 2, so 4 has got to be greater than x. Now, the other piece that limits it is 15 minus 2x. So if I look at that, 15 minus 2x has got to be greater than or equal to 0. And I solve this again, and I find out that 7.5 has got to be greater than or equal to x. The thing that's limiting this entire function, or this entire volume, maybe I should say, is the fact that 7.5 is bigger than 4. Once I have a 7.5, I can't take 15 away from 8 and able to get the length of a side. So I have to consider that x can't be bigger than 4. So this is my limiting factor right here. So keeping that in mind, my domain is from 0 to 4, including 0 and including 4, and this domain gives the box with volume of 0. Okay, so I got to keep in mind, my box could have a volume of 0. All right, now I'm going to put this in my graphing calculator. So I got my graphing calculator. I go to y equals, I clear that. And I've got this function, x, pop this over, the function's up here in the corner, x times 8 minus 2x, right parenthesis, left parenthesis, 15 minus 2x, right parenthesis. Now I've got my volume in the box, and I know what's going on. I've got that in my calculator. Now I got to consider my window. Okay, my window, when I'm looking at this, I'm kind of thinking that I'm going to have an interesting window. Let's see what I've got. That might work, what I've got going on. I'm just going to graph that and see if it's realistic. Remember, right now I'm looking at cubic. It should be, you know, a cubic when I graph. And yeah, it's going to cross 3 times. But the things I don't care about are over here. I don't care about the stuff underneath, okay? Because I know it's going to have some behaviors, but remember, I don't care about what happens when it's negative, and I care about when it's 0. So we can check out the zeros, but I already kind of know where they are. I know it's 0 at 0, I know it's 0 at 4, and I know it'll be 0 again at 7.5. Okay, so let's look at those. Let's investigate our zeros. So I go 7 calc, and I check out my zeros. So I'm going to go here. I know the first one's at 0. Let's check this one out. This one should be 4, we hope. Okay, so my first 0 is at 4. Let's check out my second 0. Okay, and as I go around in the function, I'm going all the way around. So that's 1. Now I get the other side. And my other one's 7.5. So I know where my zeros are. So I'm happy with that. But from 4 to 7.5, those are negative values. I don't want negative values in my volume. So I'm looking at second calc. I want to know a maximum. That's at 4. And my maximum's over here. I want to know what the maximum volume is. So I'm going to sit here and hit my maximum. So I arrow back over and hit that. My maximum volume of this problem is when I cut my squares out that are 1 2/3 inches by 1 2/3 inches. Okay, and my volume would be 90.74. So my x will be 1 2/3, and my volume will be coming up there. So I'm looking at this, and remember, I've got a maximum. I've checked this out, okay, and I've put that on my grapher. And how big should the squares, using my max, I've got 1 2/3. So each cutout square should have a dimension of 5/3 by 5/3 if, you know, I want to look at that. And remember, as I'm looking this over, I just pulled this problem apart, but I got a piece of cardboard and the sides are folded up to form the open box. I'm supposed to find the maximum value. That's what this is a maximum value, and my maximum value of volume is found when the cardboard is 1 2/3 by 1 2/3 that's cut out of each corner. Now, in my next one, forming functions from graphs. Protecting an antenna. A small satellite dish is packaged with a cardboard cylinder for protection. The parabolic dish is 24 inches in diameter and 6 inches deep. Okay, and the diameter of the cardboard cylinder is 12 inches. Okay, So how tall must the cylinder be to fit in the middle of the dish and be flush with the top of the dish? Well, what they're saying is I've got this cylinder, okay? This cylinder's inside my dish. My dish is 24 inches in diameter. This cylinder is 12 inches in diameter from here to here. They want to know its height inside my dish here. They want to know my height. Now, to help me set this up, I'm going to set some things up to make it a little easier for myself. Okay? One of the things I'm doing is looking at this idea is that I know that this whole length is going to be, that's the top of my box is 12. So if you envision closing that down, I've got a box here that comes down here, and this is what I'm packing my dish in. Now, inside at 6 here and here, I should have my cardboard that I'm packing in to make sure the box stays nice and firm and the dish doesn't move around. But how high is that? They want us to find this height. Remember, that's the height I've got to find. So let's talk about the equation of our parabola. And our parabola is of general form y equals k times x squared. Okay. Now I have a value that help me find k. K is my multiplier, either vertical stretch or vertical compression. We'll see what's going on. But if I put this in, I know 12 is my x value and 6 is my y on my parabola. Those are right here. This is my x, this is my y. I'm not sure why I put h, but this is my x, this is my y. And I know that's 6, 6, by the way. So I'm looking at this and I pop these in. So I'm here and I solve for k. So I got 6 divided by 144. And I reduce that and I find 1/24 is k. So my parabola has a formula of y equals 1/24 x squared. Okay. Now, I know this formula. Why do I want to know this? This distance from the x-axis to the edge of my parabola, I want to find out so I can find this distance h. Okay, because I know from here to the top it's 6, because it's 6 by 6, that goes all the way across. I just want to find out how high it is. So now I'm going to use that information at 1/24 x squared, and I want to find how high my parabola is at x equals 6. So I'm going to pop that in. So I got 36 divided by 24, which gives me 1.5. So at that point, I know it's 1.5. So what I want to make sure you see is that this is 1.5. This spot right there is 1.5. And I know 6 minus 1.5 gives me 4.5. So that is the height of my disc inside. So this is going to be 12 by 4.5. That's how I found my 4.5. So my final answer, now 6 minus 1.5 is 4.5. I've got a disc, cylinder going around, a hollow cylinder going around. So my final dimensions on my parabola, the dimension of the cylinder packaging, this dimension of the cylinder packaging, cylinder inside the dish. You know, somebody's got to pay attention to what he's typing. The dimensions of the cylinder inside the dish, the dimensions of the cylinder packaging inside the dish are diameter 12 inches and height 4.5 inches. Okay, and that's what we were supposed to find there. Now, forming functions with verbal descriptions. This one's kind of involved. So there's a couple things I want you to do. First, the volume of a cone. Volume of a cone is 1/3 pi r squared h. In this problem, a grain is leaking through a hole in a storage bin at constant rate of 8 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone always remains equal to its radius. So the radius is equal to height. So I've got that represented that R is equal to H. And I'm going to take this equation, that 1/3 pi r squared H, and I'm going to substitute into R, that R and H are together. That becomes 1/3 pi H cubed. Okay, so that's my volume of my pile. Now, keeping in mind what's going on, I have a grain bin, whatever that is. So my grain bin is leaking. So this is leaking at 8 inches of grain per minute. Okay, so it's leaking at 8 inches of grain per minute. Okay, and it's making this pile, this conic pile, that has a height h and a radius h. Okay, thus we can find the volume by h cubed because my height is h and my radius is h, and that's where we come from this. Okay, now when I'm looking this over, let's see if we're missing anything. The grain is leaking through a hole in a storage bin at a constant rate of 8 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone always remains equal to its radius. If the cone is 1 foot tall now, how tall will it be in 1 hour? Okay, so right now it is 1 foot tall. Okay, so in 1 hour, how big will it grow? Now, one of the concerns here is we need to be able to add in some volume. So we're going to find out how much volume will grow in an hour. So growing volume in an hour, I've got 8 inches cubed per minute, and I have 60 minutes in an hour. So in an hour, it's going to grow to 480 inches cubed. So it's going to increase the volume by 480 inches. Okay, but now keep in mind, I was told here the original volume, and my original volume I know is of 1 foot, and everything's in inches. So my original volume, being that I've got 12 inches right at initially, because I was 1 foot high, my original volume is 576 pi inches cubed. Now I'm going to leave that pi because I want to have all my value in there. I'm not going to multiply it out. I suppose I could if I wanted to, but I'm just going to leave it in there. So now I know what this is my starting volume. This is how much it grows in an hour. Now, I've got some concerns here. If the cone's 1 foot tall now, how tall will it be in 1 hour? Now, I've got to add those together, but I got to do some things. I'm looking for height, and I want to relate my height of my cone in terms of its volume. So I'm going to take this 1/3 pi h cubed and solve for h. So I have h in terms of volume. So what I'm going to do is multiply by 3. So I've got 3v equals pi h cubed. Divide by pi. So I've got 3v over pi equals h cubed. And now take the cubic root. So now I have the cubic root of 3v over pi is equal to h. Now, keeping in mind, I now have my height of my cone in terms of volume. Now, in 1 hour's time, how much volume do I have? So in 1 hour's time, so the volume in 1 hour total is 576 pi, but it's 480. Okay, and that's what it's equal to here. That's my volume. I'm just going to add those two together. So that's my V. So now I have a relationship that I can relate my volume. I know H is equal to the cubic root of 3 times my V. Now remember, this is my volume, okay, in inches cubed. I just put this in my calculator, and I can tell that I have my height is now 12.97 inches. But now, it's not helpful if you're not having fun with your calculator, so let's talk about our calculating and see how that would work. So I'm going to go 7 quit. I'm going to clear that out. I have the cubic root, and I'm just going to do it with powers. So I've got 3 times the quantity, 576 pi, second pi, plus 480. Okay, I'm going to close that, divided by pi, and then I'm going to close that, and those are all in, raised to the 1/3 power, and hit enter. So that's 12,97899, 979 inches is the height, is the height of my cone of grain after an hour. One hour. Okay, so that's it. That's what I've got for that problem. I hope it makes sense. Read through it a couple times, and I'll talk to you about it again. Now, the next thing we're going to do is a linear regression. Did I say linear regression? I meant stoichiometry. Example 5, letting units work for you. How many rotations does a 15-inch radius tire make per second on a sport utility? Well, the things I've got going is my circumference is 2 pi r. I've got a radius of 15 inches. So I plop those in, and I know my circumference is 30 pi inches per rotation. So it goes once, I'll go 30 pi inches down the road. Almost, more than 90 inches I'll be able to go each time it rotates. Now, keeping in mind, I want to go 70 miles per hour, and I have a couple things going. I've got to be able to take my miles, bring it down to inches, and my hours, bring it over to seconds, okay? Because how many rotations does a 15-inch radius tire make per second on a sport utility vehicle traveling 70 miles per hour? So the first thing I'm going to do, I'm going to look at the fact that there are 60 minutes in an hour. And the reason why I decided to set this up this way is that hours will cancel. Now I've got minutes, but now there are 60 seconds for every minute. So I got 1 minute over 60 seconds. And I've got the minutes canceling. Now I have my speed in 70 miles per second. Okay, and remember that's 3,600, and I'll have to divide that into 70. So how many miles per second am I traveling? But now I've got to get it to inches because, excuse me, I lied. I've got to change miles to inches so I can give it in revolutions. I want revolutions on top. And I have 30 pi inches per rotation, or what I'm going to use is 1 revolution is 30 pi inches. So I'm going to take miles, and there are 5,280 feet in 1 mile, so miles on the bottom, okay? And there are 12 inches per foot, so feet are on the bottom. And now I know that I have my 1 rotation is 30 pi inches, okay? So I brought things down, and I'm going to go for this part. I'm going to be talking about my feet being knocked out, my miles being knocked out, my inches are out, and now my final answer should be rotations per second. So now, my last thing here is I pop this in my calculator and I get 13.0719, which is 13.072. So I've got 13.072 rotations per second for a 15-inch radius tire going 70 miles per hour. Now, I'm going to pull up my calculator and we're going to construct function from data. And I'm going to make a scatter plot of this data and be able to pull this stuff off with entering it in my calculator. Now I've placed this information as L1 and L2 for my low and high for each city here from 9,999, and I have preloaded my calculator. If I can get to my calculator. I preloaded my calculator, and I'm looking at the idea that I'm going to put in my statistics. So in L1, I put in everything 70, 62, 52, 70, 68, 70, 61, 82, 64, 65, 54, and so on. In L2, I've done 86, 80, 72, 94, and all the stuff in the next list. So I have 20 entries in each list. Now, I want to be able to show you my scatter plot. So I have a second scatter plot. And my plot is off right now, but I'm going to turn it on. And I'm going to hit graph. Oop, I got to get rid of my old plot. So I'm going to enter, I'm going to clear that out. And I got my plot, and I'm going to go zoom fit, which is 0. Oh, zoom stat, I lied, which is 0. So that's my scatter plot, okay, of all that data. And let me check my window. And I started at max min of 46. Let's go 0, so I can see, and my max is 0, so I can see my XY coordinates. So there's my data. I want to be able to do a best fit line to that data. Now, to do a best fit line, I go to stat, I arrow over the calc, and I pick 4. My data was in L1 and L2. I want to go down here, and the stuff I'm doing right now is right here. I want stat to calc to number 4. My X list low is L1, that's a low. My Y list, my highs is L2. I'm storing a regression equation, and I want to store that in second vars over there, enter, and Y1. So I'm going to hit calculate. And this is going to calculate my numbers, and that's the values I've got. And I'm going to use this regression formula. I've got it stored in Y1, and I'm going to graph it, and that's the regression line I just got. It's mimicking my data that I have. And what you're seeing here is this information right here. Now, keep in mind, the information I had was that formula. It's in my Y1. My calculations on will completely be on my GC, and there's 2 ways I can do it. I can put my 46 in, and I should come back up here for a second. My records in 1.2 records the low and high daily temperatures observed in 9/9/1999 in 20 major American cities. Find a function that approximates the high temperature Y as a function of the low temperature. Use this function to predict the high temperature that day for Madison, Wisconsin, given that the low was 46. Well, I did my regression data. This is my linear relationship, and now I'm going to go after my final answer. So I've got this going on. And I'm going to place into my graphing calculator, since I already have that data in there, I'm going to go second quit. In my vars, Y vars, enter. I'm going to hit Y1, maybe, if it lets me. And I'm going to put in function notation, 46. And that'll return 67.62988. But so the low, if I go and put it in Y1, 46 will equal 67.630 degrees, okay, Fahrenheit, and that'll be the high temp in Madison, Wisconsin that day, okay, based on the information we have. Okay, now, there's a setting in your calculator I want you to be aware of. Well, I'm not going to talk about the setting. I'm going to talk about the fact that there's a bunch of regression models that we're going to use. Okay, we have a bunch of regression models, and these are the regression models that we can possibly use. And based on the information that we have, we could use one or the other. But when you're using regression models, use the lowest version of the regression model that best represents your data. You don't want to get fancy. You don't want to go crazy. You just want to go simple. Okay? And you can read through these possible models. They're all available in your calculator. One of the things I want to bring up is a correlation stat. And we don't have this in yet, so we need to do this today on your calculator. So you're going to go to catalog. That is second 0, and you're going to go to catalog, and you're going to arrow down to diagnostics on. So I'm going to keep going down to something called diagnostic on. Whoops, I have a fat finger, so we're going to do that again. Second 0, and go down. And I'm looking for D, diagnostic on. We're almost there. Diagnostic on, and hit enter. I'm going to hit enter again, and it says done. Now after it says done, I'm going to rerun this stats data. I'm going to go under stat. I'm going to go over to calc, hit 4, arrow down, hit my vars Y1, that's where I want to store it, and hit enter. And then calculate. Now when I calculate this time, you're going to notice that now I have an R value. This R value, the closer this is the 1, the better it approximates my data. Okay, I'm at 11% off. Okay, give or take. That's what they're saying is how far off I am on my data. Since this is a linear relationship, I will use R. If it's a quadratic relationship, I could use R squared, but the closer R squared is the 1 means that closer the data is coming in. But the R to the first power is correlation coefficient. R to the second power is the coefficient of determination. So we should be able to have these on our calculator and be able to talk about how good data is fitting our model. Okay, today's assignment. Here, I can bring this back over. It's right here for section 1.7, and there they are. I hope things are going well. Have a great day.